In this problem, we have identical masses, A and B, on two inclined planes, no friction here, and the inclined planes have the same height. We're going to release each one from rest, and number one, draw a free body diagram for mass A and a separate free body diagram for mass B. And then number two, prove using first principles if one block is moving faster at the bottom of its ramp, or if they both reach the same final speed. This is a nice question where you can get some practice remembering the major concepts and first principles that we've learned both in the unit on forces and also in the unit on kinematics, and kind of combining them together to analyze this really good question. So pause the video, take some time, get a nice fresh piece of paper out, pen or pencil, give yourself, I don't know, 10, 15 minutes or however long you need to really think about this one, and try as hard as you can to get past that initial stage where you have a general sense and intuition of what you think is going to happen, to analyzing from first principles and using these critical thinking and logical skills that we've been building up here in physics. We have processes, we have equations, we have concepts that will guide our thinking, and I'd like you to continue to experience that. All right, so pause the video, and then we'll come back and we'll take a look together at hopefully what you should have come to realize. So here's the answer to the first question, drawn two free body diagrams, and I'm also drawing the inclined plane just to help us visualize it as well. Usually when we draw a free body diagram, we idealize the objects as points, and you would want to do that if you had like a completely formal final free body diagram. But today I'll just do this on the inclined plane because it's helpful when first learning. And what you notice that I have not done is I haven't drawn the components of the force of gravity. And on the quote-unquote free body diagram, we never want to draw the components. However, when first learning the inclined plane, it is very helpful to visualize that. So I'm going to go ahead and do that anyway right now, even though you would not want to draw the components on a final formal free body diagram. Let's go ahead and do that and make sure I've done this right. So I'm going to break down this gravitational force vector into what I'm drawing right now, which is called a y component and an x component. So I have my coordinate system over here, y and x, orienting things. Same on the other inclined plane. I won't draw it on there because it'll clutter up the diagram. But importantly, I kind of did this by eye, but the length of this vector here, the normal force, that has to balance out with this y component of the force of gravity. And if I wanted to give these things proper subscripting, I could call this one the force of gravity in the x direction, and this one over here, the force of gravity in the y direction. And just looking at my picture, it looks about right. Maybe this is a little bit too short, but oh well, it's roughly the same. So I'm just going to go ahead and put a line like this, to show that they are equivalent. All right, balanced forces in the y direction. And again, why? It's because there's no motion at all in the y direction. So here's the y direction, and it's at rest the whole time in the y direction, since the y direction is now rotated. And then we have this component here, and that's causing that force parallel to the ramp, accelerating the mass down the ramp. Awesome. Likewise, we get the same idea over here, but what I wanted you to hopefully draw out and see is that in this case, when we do our components, we need to draw our right triangle, of course, and have everything parallel and perpendicular. I guess I will draw this here. So there's the y direction, and then here's the x direction now. So we can see it's a lot steeper. Hard to draw this in, but y and x like that. And you can see we have a much shorter component for the force of gravity in the y direction. Oops. And then the force of gravity in the x direction is much steeper. And that, of course, means we're going to have a much larger force parallel to the ramp pulling us down. So we'll want to conceptually think through what that means. Likewise here, these two are balanced. Same thing, no motion at all in the y direction. So check your work and see if you were able to get this correct. Also notice how the force of gravity vectors are identical. They both point straight down, and they're both the same size because the mass of each object is identical. So a lot of little details to get right here. And pause the video, like I said, check to make sure you got it, and then we'll move forwards in the problem. All right, next quick little thing we'll do, just a nice little proof here, and we'll prove that these angles are identical. So the angle of the ramp is the same angle that exists between the force of gravity vector and this y component of the force of gravity right there. Pause the video if you can't see it and try to work out and prove with geometry or trigonometry why these angles have to be the same, and then we'll do it together. Go ahead. All right, let's take a look. Now, one of my favorite kind of real quick ways to do it is just imagine the ramp gets shallower. So just kind of pull this thing down. And if you do that, you'd watch this angle get a lot shallower, and you'd also watch this decrease as well. And if you were to expand that, make the angle much steeper, you'd see this angle grow, and this angle would grow as well. If you don't believe me, pause the video and draw it out, and you'll get a sense that, that happens. But to really prove it, we need a little bit of math here. So the first thing to do is look at the right triangle, and you should know that this here would be 90 minus theta. Next thing would be to realize that this here is a right angle. And notice that as we go from here all the way over to that, right, that's 90 degrees. And that has to be the summation of whatever these two angles are. So if you just add those two angles together, 90 minus theta is the first one. Add that to theta, and that is equal to 90 degrees. So that means that we have to have equal theta right there for this mathematical expression to work. And essentially, we've proved it in a quick way that that angle is theta. Now, the next thing I like to do is to try to draw out things a little bit more detailed in terms of what I'm trying to solve for, etc. So you can see here, I've got the incline over on the right, and I'm calling that distance d. So that's how far this is going to slide down. It begins at rest, so we might as well put that up here as well. And it reaches some final velocity, and that's really what I'm interested in here, trying to compare the final velocities of A and B. I know it's accelerating the whole time, and it's just moving in a straight line while accelerating with a constant acceleration. The acceleration value is not changing. And we'll get the value of the acceleration or an expression for it in a second. But we take this first step just to help us understand where we need to go in the problem. So it's looking like I need to come up with an expression for the final velocity, and I have uniform acceleration here. So how do I do that? Well, the equations of motion will help us. Specifically, the third equation, or what I like to call the third equation of motion. And that one states that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement, which I'll just write as delta x. We notice that the object is moving down the ramp, and that is in the x direction, so we'll put some subscripting here for that as well. Even though we're normally used to the x denoting horizontal motion, we can see in this problem we're using x to communicate something different. All right, so we've got that as a nice tool for us to use in a little bit. Next thing is just kind of go through each term and remember what we're solving for and what we have. So let's do that. We're looking for final velocity. The initial velocity we certainly know. We can cross that out. It's 0. And then we go again term by term. The acceleration, we need to find an expression for that so we can compare both of these blocks. And then we also need an expression here for the displacement of the object, which is just going to end up being this distance here. Okay, so maybe pause the video now if that gives you a little bit more help if you weren't able to do this on your own. But if you do have a final solution, of course, then just continue along and we'll double check things. All right, cool. All right, moving forwards, kinematics has given us this equation, and now we're going to transition into using Newton's laws, specifically the second law. I've labeled our diagram over here, so we have the force of gravity pulling down. The magnitude is just mg, the weight of the object. And when we break that up into our components, x and y, with our rotated coordinate system, we have mg sine theta pulling down, and then mg cosine theta. Or I should say, let me back up. Mg sine theta is pulling parallel to the ramp down the ramp, and mg cosine theta is pulling down in the sense of in the negative y direction, which is balanced out with that normal force. Continuing along, we note that there is only one force parallel in the x direction here, and it's this mg sine theta. So we can write that, and if we want to be real formal about it, we could write out this force of gravity in the x is now equal to max. Plug in for it, mg sine theta. Get the sign right. So double check the sign. We're choosing down the ramp to be positive, and sine of theta for angles between 0 and 90 degrees is going to be positive. Mass is positive, and g is always a positive value by convention. So we're good to go with the sign check. Now we continue along, and we'll cross out the mass. Interestingly, the mass does not affect the acceleration at all in this case. And then we'll write out our result here. So acceleration in the x direction is g sine theta. Now we're not done quite yet. Now we need to use that to compare A and B and get to a final result. For the comparison though, let's build a general expression for the final velocity of any block after it has slid down a ramp of length d here. So we'll bring our third equation of motion, or what's left of it, I guess. In this case is 2 times the acceleration in the x direction times delta x. Remember that the initial velocity canceled out. And then let's start plugging some stuff in. We'll leave this squared up here for the time being. And then 2, and then we get g sine theta, very importantly, for the acceleration, and then delta x. Now we'll stop for a second and think, what should we expect to be different for the two cases? We'll look at what we have. Well, 2 is a constant, g is a constant, but we know the angle is different between the two. It wasn't really stated what the angle was, but the sine of theta, of course, would be a different value. And then that leads to this final term here, the displacement of the object. So we really have to stop and critically think. For two inclines of the same height, do they have the same lengths down the incline? Pause the video and think about that for a second. It should be obvious, I hope. Go back to the picture you drew for the first incline A and incline B. And notice how they both have the same height, up and down, straight vertical, right? But is the displacement down the incline in the x direction the same or different? Pause the video and make sure you can see that before moving on. All right, well, I've drawn both of them out here. The constraint of them both having the same height with different angles here shows very quickly that they're going to have different displacements in this x direction. Even though they both have their own kind of x direction with the rotated coordinate system, this is the distance, or this is the direction that we're interested in for this guy, and this is the direction over here for that one. So because the angles are different and the heights are the same, that's going to mean we have to kind of drill down further into this delta x and get an expression for that in terms of these other variables. So we're looking at an equation where we can adequately compare things together. So let's do that, and all you need to do is some simple trigonometry to get that. So pause the video and see if you can figure out what that expression would be. You're trying to produce delta x is now equal to something that is shared here by both of these inclined planes. Pause it and try. So just simple trigonometry. We have a right triangle. This is delta x, this is h, and we have theta. So sine of theta is opposite over hypotenuse, height over delta x. And then we can just solve for the displacement down the ramp, and we get the height of the ramp divided by sine theta. And in the back of our minds, we're remembering that h is the same for both of these inclines. That's going to turn out to be important. Now we'll jump over here. I've just rewritten this formula over on the right-hand side. And now, hopefully the path should be illuminated for you if you haven't seen it quite yet. But what would you do next? How would you go all the way down to prove the final answer to our question? All right, so again, if you haven't got that quite yet, pause the video and try it now. And if not, we'll continue here. Okay, so we can now plug in our expression for the displacement for any incline that has some height h and obviously an angle. And we'll plug that in. So we get 2g sine theta from before. And now this is just an absolute incredible moment. That happens all the time when you're doing theoretical work. You just keep pushing and pushing, writing things out, drawing as many diagrams as you can, coming up with as many equations as you can, and then trying to kind of put them all together. And often what happens is you get these incredible cancellations. And that finally shows you the path forward. It's kind of in one foul swoop sometimes. Whatever, I'll just write it in red. The final velocity squared in the x direction is 2g h, incredibly. And now let's take our square root, and we get that the final velocity in the x direction is the square root of 2gh. We'll put a box around that, and we'll make a note that we used kinematics and forces, specifically the analysis of the inclined plane, to produce something that is incredible. And what it says is that as long as the heights are the same of these inclines, of course g's the same, we're on the same planet Earth, right? As long as the height is the same of the inclines, they're both going to reach the same final speed when they get to the end of their respective ramps. Forgot the equal sign there, oops. And that's an incredible fact. And if you go back to one-dimensional kinematics, where we had like a ball and we dropped it from rest, like this, a height h above the ground in a gravitational field where it's just falling straight down, that we get the same result. So the final velocity here, right before hitting the ground, also be square root 2gh. And you can prove that just using the third equation of motion, like we've done before, with our acceleration being g straight down, and then our vertical displacement would be h, and you could plug that in and produce the same result. So that's pretty incredible that regardless of if you drop something from some height h or you let it go down a ramp that also has the same height h, and the angle of the ramp could be different, you're still going to get the same final speed at the bottom of the ramp. We didn't come to this analysis from like a general vague intuition about what we feel is happening. We came to it from fundamental concepts, first principles, and a logical analysis from beginning to end to produce new knowledge using both kinematics and forces over here. And this is what doing physics is all about. So there's the answers to our questions, and I want to leave you with one little bonus question as well that I didn't give you in the beginning. And I want to do this one now because it shows you another skill that's helpful for really quick thinking in physics, which is also important. We did some methodical step-by-step thinking, which led to some new knowledge, but other times it's helpful to just think quickly but correctly using some simple ideas. So the question here, and I'm not even going to draw anything quite yet because I want to help you practice visualization, but what about time? So same scenario, identical masses, the same planes that we drew in the beginning today. And the question would be, would one of these blocks reach the bottom of its inclined plane, assuming they both started from the top of their inclined planes? Would one of them reach the bottom of its inclined plane in a faster amount of time, or would it be a tie? Would they both get to the bottom in a faster amount of time? Right? See if you can pinpoint a real quick and easy way to answer that question to where you 100% know that has to be the right answer. Okay? Pause the video, think about it, and then I'll show you a skill in order to do that. All right, here it is. It's called extreme thinking. Keep everything else the same, just change one thing. So what we've done here, of course, is we've kept the height the same, the mass the same, gravitational field strength the same, but we've really have done some extreme angles, a very, very shallow angle, and then a very, very steep angle, almost 90 degrees. And if you just look at it quickly, you can clearly figure out that, well, obviously, if there's no friction or air resistance or anything like that to worry about, we can see that this one is going to get down here much quicker. Now, if you want to prove that with the actual equations, you can also do that as well. Which equation would you use to get to the heart of it, and what kind of relationships are important? Well, you'd use an equation that has time in it. So I would use the first equation. The final velocity in the x direction is the initial velocity in the x direction plus acceleration in the x direction times the amount of time. Clearly, we have no initial velocity. And remember, the x direction is not horizontal. It's the direction parallel to the ramp. So we want to be real clear about that, just so we don't confuse ourselves. Here's x and here's y. And then we can solve for time. And so let's do that together. Pretty easy. And now this is kind of a moment to where you can see how work we've done before, just before in this problem, is now paying off. And if we wrote that down and we kept it all organized, we can now use that work. Now, before kind of plugging in, we can essentially do the thinking pretty quickly. We know conceptually that the numerator here is going to be the same for both. Final velocity in the x direction is the same. We just proved it. So if this is the same up here, then we need to conceptually think about the accelerations. Well, the block here in the very steep incline is going to have a much larger acceleration. G sine theta was the acceleration. And so, therefore, if this acceleration is larger for the steeper incline, we have a larger number in the denominator, the same number in the numerator, and that's going to lead to a much smaller amount of time, or quicker, to say. Now, to continue and to kind of get everything out in the end here, oops, we can plug in our previous result, 2gh, and then divide by g sine theta. And this is not a very good form. What I would do is square both sides of the equation so you could not have a g upstairs and then a g downstairs here in the math. So let's go ahead and do that. All right, so if you follow along with the math here, I squared both sides, so t squared down here, and then that allows me to cancel out this g with the squared there. Don't forget the sine squared theta on the bottom. And then when we take the square root again, we can consolidate this 2h and g all under a radical. And then when you take the square root of 1 over sine squared theta, you get 1 over sine theta like this. So we get an expression that is very similar to something that we've seen before. Where have we seen this? Well, we know that if we drop a ball from rest, from a height h above the ground, so at rest up here, the amount of time it takes to fall from rest right before hitting the ground is 2h over g. So it's pretty incredible that we're seeing that same expression show up here. But it's modified a little bit, and it's modified by this factor of 1 over sine theta. So since that's something new, we probably want to do a couple little tests to make sure it's reasonable. One such test is to set theta equal to 90 degrees. So we'll go ahead and do that here. And that would mean we would get, or the sine of 90 degrees is equal to 1. So you would get 1 divided by 1. And that would be an incline that is not really an incline. It's just a vertical drop off with an angle of 90 degrees. And that would be identical to dropping something at rest from above the ground to height h. So we're getting exactly the same expression, square root 2h over g. What about if theta was really, really small? Well, if we try 0 degrees, we kind of get into a problem. Sine of 0 is 0. So then you get 1 over 0, which approaches infinity or is infinity. I don't want to get all like undefined in math and stuff like that, but we'll just say infinite, right? And then what's 1 over, or what is something times infinity? It's infinity, so it would take an infinite amount of time. It doesn't really make sense because we have a flat incline, or an incline with 0 degrees as its angle, and so there would be no force at all, and it would move. So it kind of just breaks down, but just imagine a really, really small angle, something really close to 0. So you're seeing in the limit that we kind of approach 0, it would take a really, 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 really long time for this thing to slide, which makes sense. Cool. So we're seeing then that this extra little factor over here kind of lines up with some general simple ideas about what we should expect. And it's a nice check to see if we've done it correctly. Great. All right. Well, we've really done some nice thinking here. We've gone all the way from the initial question through first principles, major concepts, kinematics, forces, did everything in variables, created some expressions, looked at those expressions, analyzed them, try to figure out what they meant, checked them with our intuition, also kind of checked them with other physics that we've done before in the past, so you can see the real value in doing these great problems, recording them down, and kind of doing them in the right way, because now you have this background and something to kind of relate what you're currently doing to. And then over time, you build up more and more knowledge, and kind of this web of information and skill develops. And you're just that much better at encountering your new physical scenario that's a little bit different than anything you've seen before, right? So I hope in this last little bit here before we end the video, you're seeing how you need to go through and actually do the thinking yourself and build up these skills over time, because then you just get better and better at this. And it's really cool when it all comes together, especially with a really difficult problem that you've never seen before and you're just able to do it. So hopefully you had some success, maybe not every single question here, but some partial success at least with parts of the problem, which is great. And we'll continue along in our journey to keep doing well here in physics. And take care, and we'll see you next time.